are focusing these type of substrates. So it may be a substitution nucleophilic mechanism. So similarly, if it is the previous mechanism we were discussing on previous slides, because if it is a sp3 hybridized carbon system, it may undergo nucleophilic substitution. You have seen these different mechanisms of nucleophilic substitution reaction taking place on sp3 hybridized carbon. Same sp3 hybridized carbon, if connected to a carbonyl carbon, it is connected to a nitro group, it is connected to a imine, or it is connected to some other functional groups like you have seen which undergo tautomerism. So such carbon can also undergo substitution, but it is electrophilic substitution, electrophile reaction, because sp3 hybridized carbon becomes electron rich rather electron deficient, you have come across. So in this case, uh, I am just focusing as per your syllabi. The syllabi only include keto-enol tautomerism, but it is not limited to keto-enol tautomerism, because it may be different. Let's say here rather keto-enol tautomeric form. If we are having a nitro, si nitro equilibrium or tautomeric forms. Similarly, we have enamine and imine tautomeric form. Similarly, we may have a uh, nitroso-oxime tautomeric forms, etc. So these are so there are some other tautomeric form you have already come across in previous semester. So all such tautomeric form also undergo electrophilic substitution reactions. All right. So as per mechanism listed in the syllabi, so there are some by name reactions given. So let's say first Claisen condensation, similarly Claisen-Schmidt condensation, Perkin reaction, Reformitsky reaction, Stobbs condensation, Darzin's reaction, Manish reaction, Wittig reaction, and Novalengel's reactions. These reactions are by name. These scientists have a big contribution towards understanding these electrophilic substitution mechanisms. So in all these cases, we are having carbonyl carbon. So the source of carbonyl carbon is changing, and you shall see that it is very interesting chemistry in all these cases, but they are by name. So on the basis of different scientists, they have discovered. So if we are having a aldehyde or a ketone as a source where we are interested to make substitution, if it is an ester, if it is recoupling with another entity, etc. Aldol reaction is missing here. So because you have already come across aldol reaction, that's why I haven't included that in this case. So considering this one by one, in all such mechanism and listed here, Claisen-Schmidt, Perkin, Reformitsky, Stokes, Darzen, Manish, Wittig, and Novalengel's reactions, in all of these cases, we are having this group keto form. We have a carbonyl carbon. Now, what carbonyl carbon is? Maybe this R group is hydrogen, mean it is an aldehyde. This R is a alkyl group, mean it is a ketone. This R may be an ester, alkoxy group, mean this is a ester group, etc. So there are various possibilities. It may be aldehyde, it may be ketone, it may be ester, and it is going to react with an electrophile. Electrophile may be electron deficient entity. Again, another carbonyl system. All right. So we have a variety of different carbonyl carbons depending upon their structures. So let's see first the Claisen condensation. So what is Claisen condensation? In Claisen condensation, we always start with an ester. So Claisen is the name of a scientist who was basically a German chemist. Rainer Ludwig Claisen. This is his complete name. In put forward this his uh, or shared his finding in 1881. What happened? You see, this is a carbonyl carbon. Next carbon is sp3 hybridized carbon. This carbon is when reacted with a base. Normally, in these cases, alkoxides ion are being used. Alkoxide ion, let's say if we are having this any alcohol, let's say this R is ethyl, so this is ethanol. When ethanol is reacted with some, let's say sodium metal, so sodium metal lose electron which hydrogen gains, and hydrogen leave in the form of atomic hydrogen, resulting in the formation of ethoxide ion. Sodium shall be the counter ion, ethoxide ion shall be generated. So this is how this is going to remove in fact. So alkoxide ions, this R may be methyl if we are starting with methanol, ethanol, isopropanol, propanol, and similarly butanol, tertiary butanol. So many different alkoxides are being used. You see, in all of these electrophilic substitution reaction, mostly we are starting with alkoxide ions, mostly. So this alkoxide ion is used as a base. This base picks up the enol form of this. You shall see the mechanism. So it generates enolate, a negative charge here. So that negative charge here donates back, and this pi electronic density transfers to another entity. Basically, you see this molecule is containing a nucleophile. All right, this carbon is acting as a electron rich entity, and same substrate is acting as a recipient electrophile. So we are getting this product which is called 1,3-dicarbonyl system. This is a 1,3-dicarbonyl compound, mean 1 and 3 position we are having. So just focus this molecule, this part of the molecule is this one, which is a donor species, and it is adding to this carbonyl carbon. This addition is very simple. This is just like tetrahedral mechanism. This nucleophile is adding to this carbonyl, which is electron deficient, and making sp3 hybridized system, and this OR group leaves. Now, just see first, I have presented its mechanism. First of all, this ester converts into its enol form. You see, this is enol form. Enol form in the presence of alkoxide ion converts into enolate. So this hydrogen it picks up, generate a negative charge on the oxygen. This oxygen donates this electron pair. Now this carbon in other resonance form is electron rich. Now this electron rich adds to this carbonyl carbon, which is following a tetrahedral mechanism. So rather it reacts because this carbonyl carbon you have seen, this is also electrophilic, electron deficient. This carbon is electron deficient because this is bonded with this, double bonded with this oxygen and single bonded with this oxygen. So it means 3 bonds this carbon is making with oxygen. So it is highly electron deficient. So that's why this carbon donates electronic density here to an electrophile. This is an electrophile. So tetrahedral mechanism follows this carbon. This is just like a nucleophile bonded to this carbon as well. This O negative donate electron pair back, and this group, alkoxy group, leaves this molecule. So what we get? We get this carbon, which is this carbon. All right. This carbon is bonded to an electrophile, which undergo first addition, next elimination, resulting in the formation of a new carbon-carbon bond. This is a new carbon-carbon bond between the two entities. One is electron rich, other is recipient only, which have no enol form in fact. So this is the new bond formed between the two entities. And what this results, if we look at this molecule, esters are always terminal. So this is carbon number 1, this is carbon number 2, this is carbon number 3. So we have obtained 1,3-dicarbonyl system. So Claisen condensation is very, very useful in producing a 1,3-dicarbonyl systems like this. This is the unique feature of Claisen condensation. You shall see in all these by name reaction that I am proceeding further. Just we are having a different kind of substrate, a different kind of electrophile. These are keep changing and we are getting a variety of different products. Otherwise, mechanism is same. Mechanism means the keto form, enolate of a carbonyl system shall react. The alpha carbon, there should be one alpha hydrogen present at this position. If there is no alpha hydrogen present here, it shall not undergo such type of reactions. We must have one hydrogen so that it can tautomerize to this form. We must have one hydrogen here. If there is no hydrogen, it shall not undergo such type of additions. Now, let's see a few examples. We have, this is an ester, but focus here, this carbonyl carbon is attached with oxygen. Other side, this is attached with this phenyl carbon. This carbon doesn't have a hydrogen. So it is not going to form tartomeric form. It is not going to form enol form. So it is not going to react. This is just a recipient in fact. Recipient means it is having a carbonyl carbon, so it shall in fact take this electron pair off. All right. And in this molecule, you can see we have a carbonyl carbon. One side is a tertiary carbon, other side we have our alpha hydrogen is attached. Now this alpha hydrogen shall be converting into tartomeric form, which is a enol form. Enol form shall react with this base, sodium alkoxide, any alkoxide. We may have a methoxide, sodium ethoxide, etc. As we are going to increase the size, it shall make steric hindrance. So ethoxide and methoxide are normally being used. So first of all, it is going to pick up this proton from this enolic proton, and then we shall get a negative charge here. So that negative charge shall come across here, and double bond here shall add to this carbonyl carbon in very similar fashion like this. And it shall result in the formation of this molecule. Now, this one I have presented, this is a donor species presented in a green color. This is the donor species. This is phenyl group, carbonyl carbon. This is a carbon which is active component, sp3 hybridized carbon, right? sp3 hybridized carbon, electron rich, reacting with an electron deficient center, which is an electrophile. So this molecule is you can see, this is simply color shown with blue. This is it has lost this ethoxy group from this position. So this is in fact a 1,3-dicarbonyl system. Again, you see 1, 2, 3, 1,3-dicarbonyl systems. So this is between the two different molecules. This reaction, which was patent for Claisen condensation, in which he used ester condense with the esters. Ester generate enolate, and enolate react with the same ester entity. So this was done called Claisen condensation. But later on, it is also been tried with ketones reacting with esters to form 1,3-dicarbonyl systems. This is intermolecular, but it may be intramolecular. I have presented this substrate. Let's see. This is an ester. This side, it is also ester. So this carbon is having a alpha to this carbonyl. It shall have a enol form present here, enol form here. So both positions are identical, either in enol forms here or enol form here. Enolate generated here or enolate generated there doesn't make any difference. What happen in this case, let's say if enol generates here, so this shall pick up a hydrogen from here, we shall get a negative enolate, negative charge here, a double bond here. Now this carbon double bond intramolecularly, you see this is carbon number 1, 2, 3, 4, 5, 6 membered ring. All right. So this carbon shall go to this carbonyl carbon. All right. I think I have made one carbon extra here. There should be one carbon less because we are making a, if it is the structure, then we are having this carbon is making a bond with this carbonyl carbon. So it shall be, in fact, one, two, three, four, five, six-membered ring should be formed here. Six-membered. All right. So I have presented five-membered ring. So you can decrease one carbon here. But if it is you want to keep this same number of carbon here, then there shall be a six-membered ring in fact here. All right. So this carbon acting as an enolate within the same molecule, there is a ester group present. So it shall react intramolecularly, resulting in the formation of this. First of all, it shall add this, making that TD mechanism, and then this group shall leave, generating this carbonyl system here. All right. So this is the structure again. This is one, two, three, 1,3 dicarbonyl system. So if you find 1,3 dicarbonyl system, keeping in mind the best option is Claisen condensation. All right. So this is how Claisen basically make use of enolates and generated them into making new coupling reactions to generate a very interesting product that we commonly call 1,3 dicarbonyl compounds. So our system already contain one carbonyl, but when they couple with each other, we get dicarbonyl system. So this is just an example, a few example I have highlighted, but literature is full of such. Just switching over to next, Claisen-Schmidt condensation. In Claisen-Schmidt condensation, we are having an ester, but ester is just for generation of enolate. Then it is not self-coupled. It is added to a ketone in fact. All right. So if it is reacting with the ketone, this R and R, R and R shouldn't contain alpha hydrogen. If they contain alpha hydrogen, then it shall not be a good substrate in fact. All right. So what we are doing in this case of ester, let's see what we are getting in this case. It is not 1,3 dicarbonyl system. Now what is happening? It is not reacting with an ester. This enolate is reacting with a ketone. This carbon shall add to this carbon oxygen double bond. If you remember, this R and R groups are there. It cannot generate, it cannot leave any group here. Like if it is reacting with a carbonyl ester, this group is a good leaving group, but here alkyl groups are not leaving groups. All right. So we get R bond here, and we are having a OH at this position. Then we observe elimination. OH leaves from here and hydrogen leaves from there. Elimination results in double bond at this position. But this is alpha beta unsaturated esters. If you see, the outcome in Claisen condensation is 1,3 dicarbonyl system because ester is self-coupling. Ester is enolate, ester is electrophile. Same. But in Claisen Schmidt, another German scientist, so both of them provided this finding after their first reports. So Claisen Schmidt condensation always result alpha beta unsaturated esters in fact. So these are the generated. Now how, what is the mechanism? Very simple. This carbon is electron rich because it converts into enol. Enol with the presence of sodium alkoxide ion removes this proton from here, generate enolate. Now this enolate adds to ketone. Very similar way, this oxygen donate electron pair back here, and this is adding there. This is simple addition. It is not going to follow elimination in fact. So it shall result in the formation of this carbonyl. This one I have presented in blue. Right. So is everybody there? Can you see this position, slide number 5, Claisen-Schmidt condensation?
Sir.
Hello?
Yes, sir.
All right. So there was a disconnection. I don't know why. So anyhow, in Claisen-Schmidt condensation, we are starting with an ester. We generate its enolate. You see, this ester converts is in equilibrium with this enol form. This enol form, in the presence of this base, loses this H positive ion. So we get a enolate. This enolate adds to this ketone functional group. So when it adds to this ketonic functional group, you see we are getting a new bond between these. This is a donor species, sp3 hybridized carbon but electron rich. This carbon, which is presented in green, this is electron deficient center, taking this electron density from this, making a new bond. This bond presented in black. This is a new bond form. This bond, which is blue in structure, it is a donor species, and the entity which is presented in green, this is a this is a receptor. This is receiving this electronic density. This is receptor and this is donor in fact, right? So this is acceptor, this is donor, and this is a new bond formed between them. All right. So what shall happen in next case? OH in the presence of a acid concentration. So this base is neutralized. Then it is added with acid when the pH is below 7. So it is this reaction is heated. This OH is protonated in acidic medium and a hydrogen from here leaves. So it generates a double bond at this position. This is called alpha carbon. This is beta carbon. Alpha is coming from the ester and beta carbon is coming from ketonic carbonyl system. So alpha beta unsaturated double bond we are having. So this type of final products are entirely different from the Claisen products. All right. So this is another example given. This is the same substrate you have come across in previous slide, but you see here recipients are different. All right. So when we are having in this case, this is not an ester. This carbon is highly electron rich. Why? Because dicarbonyl systems like this doesn't exist in this form. You have seen, if this one of the carbonyl exists in enol form, let's say I draw a double bond here and a OH here, this carbon oxygen double bond and this enolic double bond, they are in conjugation. So when two double bonds are in conjugation, they have a little resonance energy. This resonance energy make them more stable. So this is the reason that these systems are more stable systems with one carbonyl in its form and other carbonyl exist in enol form. So two double bond in conjugation shall be more stable configuration. So it exists in enol form here. So this base picks up hydrogen, generate enolate. Enolate donates electron pair back here, and this results in the addition to this carbonyl carbon. You see, this carbon is acting as a donor species. This carbon is acting as a receptor species. So first we react this substrate with this entity and then we add this dropwise. Dropwise addition of this ketone is done. Otherwise, this shall react with this enol form of this as well, making another type of enolate. We shall react with this. That is the side product, right? So this is the Claisen-Schmidt condensation, which is normally been used. Now let's see, proceed further. The Perkin condensation. The Perkin condensation involves an anhydride rather than ester, and it is further reacted with a aldehyde. This is what we call Perkin condensation. Let's see, we started anhydride. This is an anhydride. If you remember, anhydride is a, you see, if it exists, it can exist. This is R group is same. So either enol form generate this side or enol form generate the other side. It is same, no difference. So when it couple, it results in the formation of a alpha beta unsaturated carboxylic acids, not esters. You have seen in previous case you get esters because our starting material was an ester, but here we don't have ester. Here we have a carboxylic acid. This is the difference. Second, we are having here aldehyde is used, but not necessarily aldehyde. Maybe we are using a ketone, then we shall have another alkyl group present at this position. But in all cases, either we are using aldehyde or we are using a ketone as an electrophile. In all cases, it shall be alpha beta unsaturated carboxylic acids. All right. So Perkin reaction is very important with respect to synthetic applications. So here our substrates are different. The entity, the functional group which exists in enol form is different, although it is a keto type system. But here anhydride is the substrate rather than ester. So first of all, when this substrate reacts with a base, it results enol. It exists in enol form. Enol form, this base picks up a enolic hydrogen, generate enolate. Enolate oxygen donate electron pair here, making this carbon electron rich. So this pi electronic density transferred to this carbonyl carbon and results in the formation of some entity. You shall see later how this product is being formed. So let's see the mechanism systematically. So we shall cover this Perkin condensation today, and we shall start with the other type of the electrophilic substitution, aliphatic electrophilic substitution reaction next week. This is the last we are discussing today. So just look at here the structure number one, which is an ester, which is an anhydride shall undergo generation. I have presented the enol form, but it can be enol form the other side as well because this is symmetrical. Both sides we have same alkyl group, so either it is this side or that side, doesn't make any difference. All right. So this is the enol form. I have presented that of structure number one, anhydride. And what happened in the presence of base alkoxide, it shall remove this proton from here. So we shall get a negative charge here. Now you see, if it donates electron pair, this carbon shall be electron rich. So this is how this carbon is converted into electron rich center. sp3 hybridized carbon is electron rich right now. This donates electron density to this carbonyl carbon undergo this simple addition. It is not following TD mechanism because there is no living group present in this substrate. All right. So we are getting this oxygen, this carbon, which is acceptor carbon, and this is a donor carbon. This donor carbon making a bond with acceptor carbon, and this is the anhydride. No rearrangement takes place. What sort of rearrangement? You see, this oxygen which is here is carrying a negative charge, and within the molecule we have another carbonyl of the which haven't reacted, this one. So what happens, this oxygen donate, it add as a nucleophile and adds to this carbonyl carbon, and what it shall generate, you see, 1 2 3 4 5 6 membered ring. This is a 6 membered ring which is formed, right? So this R and pH, they shall be above and below the plane. So we are not discussing the stereochemical outcomes here. In this case, this ring is formed. What happens next? Because in this case, this oxygen is present here. It donates this electron pair here. As a consequence, this electron pair transfers there, and this oxygen takes this electron pair off likewise. So when it is having this one, look at the structure here. This is in repetition perhaps. Structure number 6 and 7 are in repetition. Yes, these two are the same. Mistakenly, these are being presented in same similar way. So anyhow, just forget about this. 6 and 7 are the same. So this oxygen donates this electron pair here, generate a double bond between this carbon and oxygen because this bond is breaking, generating a double bond here, which is this one, and oxygen negative. This is carboxylic acid generated, right? So what happened in next? It becomes a good living group itself because this is an acetoxy type group. It leaves with electron pair and this hydrogen leave without electron pair. We don't need any acid to remove this. So once this is leaving, we are getting a double bond at this position, resulting in the formation of structure number 2, which is this one. So this is the mechanism how it is following in Perkin condensation. So in Claisen condensation, we are normally starting with an ester, which is in Claisen condensation, it is coupling with the same ester entity. But in Claisen Schmidt condensation, it is reacted with a ketone. All right, this is the major difference between Claisen and Claisen Schmidt condensation. In Perkin condensation, we are starting with an acid and hydride, not an ester. This is the major difference between the three different type of condensation I have highlighted here. So I am not proceeding further. We have just 2-3 minutes remaining. So we shall continue, finish this topic in next week, Monday's lecture. But if anything is not clear, session is open for questions.